Where we're going to start today is with chapter 15 on page 222. Let's back up. So we're going to talk about radiographic technique. All right, so chapter 15 in the book says image acquisition. I'm not real sure why Bushong titled some of the chapters the way he did, including this one. We're not going to talk quite as much about image acquisition as much as we are about the X-ray beam as it interacts inside of the patient, picks up the signal, and is emitted from the patient, and that striking the image receptor. Certainly, we'll talk some about the computer processing, but the title of the chapter seems like that's the majority of the focus, and it is not. It's manipulation of the image so that we control the quantity and quality of X-rays as they come out of the patient and interact on the image receptor, and how that affects the image, essentially. So what we're going to be talking about early on are the 4 exposure factors and what it is that we use to make those changes in the interactions inside of the patient, and how that's going to give us a different quantity and quality, really quantity more than quality, of photons that exit the patient and strike the image receptor. So we're going to talk about the exposure factors. We'll talk about the imaging system characteristics. We'll talk about patient factors and how that's going to relate to the X-ray, the remnant beam striking the image receptor. How we can adjust our technique to adjust to those patient factors. We'll talk about the image quality factors. We'll talk about different types of technique charts. Full disclosure, I don't know how much on technique charts you're going to really hear or read about or even test on the registry, but we're going to talk about it. We'll go back through how AECs work, and we'll touch on tomography. We won't talk just a whole lot about it because you just don't do a whole lot of it anymore. Same thing with macro radiography, but we'll talk about what those are and how they're different imaging techniques that we can use to image specific pathologies and things like that. So the 4 primary exposure factors are kV, MA, exposure time and distance. Before we get too deep into this, I want to point out something that might be a little bit confusing to you on page 222, table 15.1. Okay, so the title of that particular table is factors that may influence X-ray intensity and energy. All right, so remember, anytime we're talking about intensity, we're talking about numbers, right? So as intensity increases, numbers increase, be that MA, time, kVp, distance, whatever, just a count of photons. And what that table shows is in X-ray intensity, everything affects intensity. Right? We use one specific thing to control intensity, and that's mass, but everything affects intensity. And then energy, it may or may not change it. Remembering that the things that affect energy are 2 things. If it affects peak energy, that's kVp, and it affects average energy, then we've got some other things in there as well. But the thing I don't want you to be confused on is on voltage ripple, okay? So the perception here, all right, so we're going to have a tendency to kind of think that as we change from single phase, three phase to high frequency, then we're increasing the energy, which we are, right? We're increasing the energy and we're increasing the intensity. Okay, so you may look at voltage ripple and say, well, single phase is going to give us a lower amount than an increase in our generation, right? So single phase, 3 phase is going to give us an increase. But if you look at that, it might confuse you a little bit, and it says voltage ripple decreases. What it's talking about there, I'll kind of pull one of these up just real quick. What it's talking about there is the voltage ripple. It's specific to the voltage ripple. I need something besides blue. And I don't need a magic marker. So let's see if red shows up. Okay. All right, so single phase, remember we've got a voltage ripple looks like that, right? And then three-phase, we've got something more like, this. It's a lot of pulses. So we've got a lot of individual pulses for three-phase. And what it's talking about is the amount of voltage ripple. So on high frequency, we had less than 1%, right? Three-phase 12 pulse, we have 3 to 4%. And then we've got 14% for 6 pulse. But up here, what we have is 100%. All right? So we have 100% voltage ripple, which is a lower output than these down here. Okay? So it's more ripple, less output, than less ripple. Does that kind of make sense? Mm-hmm. Okay. So I didn't want you to get home and look at that and say, that seems kind of backwards. Not really. Not really. It's accurate. Okay. So we're going to talk about kVp, we'll talk about MA and exposure time separately, and we'll talk about distance as well. So those are the reason we call those the 4 prime exposure factors is because that's what you're going to use to control the intensity and the quantity and the quality of the X-ray beam. You don't use a change in generator, right? You don't flip a switch and suddenly you're shooting with a single phase machine. These are the things that you're going to use to control your exposure factors or your exposure. So kVp, remember kVp controls quantity and quality more than anything else. It's the thing that controls the peak energy. It's the thing that controls penetration. It controls everything. Also, it controls quantity exponentially. You remember, it goes in the same direction. You increase kVp, you increase quantity or intensity, but it's exponential, right? So it's a direct exponential relationship. So kVp does a lot of stuff. There's nothing really that kVp doesn't touch as far as brim spectrum goes, with the exception of the minimum energy, which is filtration. So as we change our kVp, we change the average, we change the peak energy, and we change the quantity of X-rays that we create. So everything changes. So it controls the energy level, which is our peak energy, but it also changes the average as well. So peak energy, average energy is our quality of the X-ray beam, our energy level. So it controls penetration. And I think in the PowerPoints online, it goes into contrast. That's really kind of archaic. kVp doesn't really control your contrast anymore. It's your computer algorithm controls contrast. So I'll probably do some more edits on this, throughout the next few weeks, and when I get it done, I'll post it. But just kind of make a mental note that if you're looking at the PowerPoints that are online, kVp doesn't have negligible effect, maybe, but not much of an effect on contrast. Okay, everything else is still valid. It controls our penetration. If we have an X-ray beam that doesn't penetrate anything, then we can't create an X-ray image of a patient. Very low quality, right? So our X-ray beam has to penetrate the patient in order for it to be useful for us. So low quality X-ray beam would be one of very low kVp that just doesn't penetrate anymore. The higher the penetration or the higher the kVp goes, the more we can penetrate, the more tissue types that we can penetrate, right? So if you're, again, back to an extreme case analogy, if we were to shoot an abdomen with 20 kVp, not much is going to get through that, right? So if we increase to 40 kVp, not much is going to get through the bony structures. We increase to 60 kVp, you can get through the bony structures. You increase to 80 kVp, you can get through the really dense bony structures as well. So the higher the kVp, the more tissues you can penetrate, and so it controls your penetration. And when we use screens and films, that's what we use to control our contrast. Higher the kVp, the more tissues we could penetrate, and the longer the grayscale will get. So the things in contrast that we need to discuss, we'll talk about here in a minute, the different words for different types of contrast and things like that. So unfortunately, the higher the kVp goes, you remember talking in the last section about how kVp increases in kVp decrease interactions all the way across the board, right? But what you get more, you get a disproportional number of Comptons to photoelectrics. So most of the time whenever we're talking about kVp, you increase kVp, you increase scatter radiation, that's what we're talking about. Relative to photoelectric interactions go down much quicker than what Comptons do. Okay, Comptons remain, I don't want to say stable, but relatively stable compared to photoelectrics. As kVp goes up, photoelectrics drop more drastically than what do Compton interactions. So as a result, what we get is a higher percentage of Compton interactions, Compton emissions from the patient compared to PEs, okay? So we say it secondarily controls quantity, even though it controls quantity more so than what mass does. And the reason we want to attribute it to a secondary status is because it controls all this other stuff too, right? Where mass, whenever you change your mass, the only thing that you change is intensity. The only thing that you change is the quantity, right? So we use mass to control that, and kVp secondarily will. If you increase your kVp, you're going to increase quantity drastically. But again, you're going to change all this other stuff as well. So for now, we don't want to use kVp to directly control quantity. We want to use mass. Again, I'm going to say this all the way through your second year. I expect that's going to change at some point in your career. The reason that we've kind of locked into kVp and its relationship to quantity and not using kVp to adjust for changes in size or tissue composition, we'll talk about that throughout the semester, is because it changes all this other stuff. And all this other stuff, in a traditional sense in screens and films, affected your contrast. Well, it doesn't anymore. It doesn't affect your contrast really much at all, right? So why not change kVp? And it's an answer I can't, or that's a question I can't really answer from an industry standard. It's just that this is the way we've always done it, right? So I expect that that's going to change, and it has to a degree. And this is kind of running down a bit of a rabbit trail that, you know, will show up later in the PowerPoints. But when we made the change from screens and films to CR, computed radiography, which is technology that unless you're at UT North, you've probably not seen. Any other place have a CR where you take the cassette and you load it into a reader, or you're just shooting all on VR? I think even the CR room out at UT North is not being used a whole lot, right? So it's out there, but it just doesn't get a whole lot of traffic. So that was the original technology that most hospitals changed to. Instead of jumping directly into DR, it was a smoother transition to CR. So the problem is that whenever we went to CR, the CR systems required more radiation than what screens and films did. But since since kVp didn't affect our contrast as much as what it did with screens and films, what they did was they increased kVp instead of increasing mass whenever they made those changes. We'll talk about that later in the semester, but increased kVp so that our patient dose didn't go up quite as dramatically. So we've seen using kVp to reduce patient dose a little bit, right? And we'll talk about how that kind of washed out with DR later on, but we've seen it just a little bit, and I think it's going to become more prevalent throughout your career until we get to a point where mass is going to remain relatively stable, and what you're going to adjust is kVp. So changes in kVp change a lot of stuff. In the X-ray tube, it changes the potential between cathode and anode, and this should be sounding kind of familiar. We just covered this in the last section. So that whenever we make exposure, the potential is released and we get kinetic energy of those electrons that travel across the tube really, really fast. But as we increase our kVp, the difference between low kVp and high kVp is that at high kVp, they're going to accelerate across the tube faster, so they're carrying more kinetic energy. So the speed of the photons, of course, remains unchanged. The only thing that changes are the same things that change whenever we're looking at different colored light. Right? So we've got white light, we've got blue light up here, we've got a little bit of yellow light, and really fundamentally the difference between those is frequency and wavelength. As the colors change, if you look at the electromagnetic spectrum, it kind of lays out the different energy levels, and within those visible light ranges, the difference, the fundamental difference between colors of light are nothing but frequency and wavelength. Remembering back to last semester, frequency and wavelength have to do with the length of the wave. So as wavelength decreases, frequency increases, right? So they're inversely proportional. That's really what happens in your individual X-ray photons is as kVp goes up, that frequency decreases. Frequency increases, wavelength decreases. All right, so behavior of photons are similar to light. What determines color of light, we just talked about that, that's frequency and wavelength. What we see in the difference, really I should say, in electromagnetic radiation is significant, right? So what we've got in the low end are things like radio frequency. Radio frequency, the characteristics of radio frequency can be very, very long. The individual wavelengths, which gives them a very low frequency. But if you look at your electromagnetic spectrum back in chapter 6, I think it is, what you get is that the frequency and wavelength of radio frequency is maybe meters long. So it's very, very long. And then when we're talking about X-rays and gamma rays, it become very, very short wavelength, very, very high frequency. So whenever we change our kVp, that's what we're doing is we're increasing the frequency, decreasing the wavelength. The higher the kVp goes, the more scrunched together they become. The higher the frequency, the shorter the wavelength. So what are the difference? You remember the difference between X-rays and gamma rays?
That's where they come from.
Where they come from, right. Where do the X-rays come from?
Outside of the nucleus.
Outside of the nucleus, as opposed to gamma rays come from inside of the nucleus. The gamma rays ejected from the nucleus of the atom. Very good. All right. So MA, when we talk about MA, we talk about intensity. That is, we don't have X-ray exposure at this point, right? So what MA does eventually is it gives us an intensity once we apply the time to it and create mass. But at the point of prep, then really the only thing that we're doing is we're heating the filament. And what causes the heat on the filament is just the friction of the electrons traveling through the filament. Remember that we've got, as I've drawn it, we've got two separate circuits. We've got the high energy circuit, and we've even got two portions to that. We've got a low voltage, high voltage portion. So low voltage portion is before the high voltage transformer, and the high voltage portion is obviously on the other side of the high voltage transformer. Then we've got the filament circuit. What you don't see in the filament circuit are rectifiers, and you don't need rectifiers in the filament circuit because it's low voltage, right? So we've got alternating current down there, and what we're doing is we're running electrons, and it's a tremendous number of electrons through the filament all at one time. So it's an inconceivably large number, 6.3 times 10 to the 18th power electrons per second. We're running a tremendous number of electrons through the filament. So it's a lot, it's a big number of electrons. The higher our MA, the higher that number is. That's representative of 1 amp. So we've got a tremendous amount of electrons going through it. The more electrons we put on it, the more heat we create. The more heat we create, the more electrons we have available in our space charge, and our thermionic emissions sent across X-ray tube. Okay? So MA just controls the heating of the filament. It places the electrons on the filament so that when we get to the point of exposure, we've got the electrons that we need to pick the way you want to consider it, push or pull the electrons across the tube to make our exposure. So at the point of the exposure, the higher the MA, the more of the electrons, the higher the intensity of the X-ray beam, and it's a direct relationship. You double your MA, leaving the mass the same, then you're going to double the output of the X-ray tube, right? So it's what we use to control intensity. So what does MA control and what does it not control? Well, potential energy. What is potential energy? It's a measure of difference between the cathode and anode into the X-ray tube. What do we use to control that potential? kVp, right? So how does mass or MA control, or how does it affect that? It does not. It has no effect on potential energy. So if it doesn't affect potential energy, how does it affect kinetic energy? Well, in the exact same way. It does not, none. So beam energy being a measure of kVp, it doesn't affect that either. So it doesn't affect penetration, except for if you can, I point this out because I don't want you to make this leap. When we're talking about penetration, we're talking about percentage of the X-ray beam that penetrates the patient, right? So if you double your mass, you make an exposure, and you get a certain number of photons through the patient. When you double your mass, you're going to double the number that penetrate through the patient, right? But it doesn't change the percentage at all. Okay, so that's what we're talking about in an increased penetration. If the kVp remains the same, if you increase the mass, yeah, you're going to get more penetrated through, but the percentage of penetration remains the same, and that's what we're talking about there. All right, so it doesn't affect penetration in that sense. Okay, so don't flip those around. So what controls frequency and wavelength? Potential energy, kinetic energy. If mass or MA doesn't do anything to either one of those, what's it going to do to frequency and wavelength? Nothing, right? So what are changes in MA control? Heating of the filament. At the point of exposure, if you increase your MA and everything else remains the same, then you're just going to increase the numbers. It's the only thing that it controls. MA numbers, time numbers, nothing else, okay? All right, so of course we have to have time. So we have MA and time together to create mass. So a lot goes into the combination of MA and time. So what we've got is short exposure times. Why would we say that short exposure times are preferred? Usually, anyway. What do you suppose?
Tube limit.
Tube limit? Okay, that's one reason. Okay. Before we get to tube limit, though, what are your breathing instructions for a chest X-ray? Deep breath in and hold your breath. Why? Why would we want the patient to hold the breath? Motion. We want to eliminate motion, right? So regardless of the patient's ability to cooperate, motion is still a potential issue, right? So, you know, if let's take it to an absurd extreme. What if we had a 1 minute exposure? How many of your patients would be able to hold their breath for a full minute? Can you? Some might, right? Some definitely not, but some might, right? So your patient's being sick, you're taking chest X-ray on them. If you had an exposure that long, motion's going to become an issue. Make sense? So we want short exposure to try to mitigate some of the danger of having motion on the image. Motion, you can affect whether or not you're going to have motion, right? Remembering you've got two different types of motion, one involuntary and one voluntary. Voluntary motion, you overcome voluntary motion with good instructions to the patient. Hold your breath, be still, those sort of things, right? Involuntary motion you can't really control with anything except for short exposure time. But still, motion is something that you can't control. You can't control. You can control the likelihood of whether or not you're going to see motion on the image, but you can't control the patient, right? So regardless of what your exposure time is, and what your instructions are, it's all dependent on the patient to be able to, be still enough that you can get an image without motion. So motion becomes the number one thing that will destroy sharpness of recorded detail, and whether or not spatial resolution, sharpness of recorded detail, and whether or not you're going to be able to see the detail that you need to see. And it's the number one thing, or the one thing that you can't control really at all. It's all in the patient's hands. So we use short exposure times even when we have patients who can cooperate, just to make it more likely that we're not going to see the motion artifact. So that helps primarily with involuntary motion, but it also helps with voluntary motion as well. If time gets too short, but especially if mass gets too low, then we can introduce what we call quantum model. So quantum model, I think I put a couple of videos in Canvas. Quantum model is kind of so breaking the words apart. Quantum, what does that sound like? What's that? Quantity, right. Right, it's quantity. So have you ever heard of something to have a modelly appearance? Anybody ever referred to that? You got a patient kind of splotchy looking, they have a mottled appearance to their skin. That's what model means, is a splotchy appearance. Okay, so you put the two together, you got a splotchy appearance because you don't have enough of something. Okay, well, what controls the enough in our X-ray beam? Enough being quantity, quantity being mass, right? Quantity being mass. So we get a splotchy, speckly appearance because we don't have enough mass. That's quantum model. What you're going to find is that quantum model is starting to be a little more theoretical than what we see in actuality. Our image receptors, especially in DR, digital image receptors, are so sensitive that it's hard to introduce quantum model. So all of the stuff that we're going to talk about, in theory, could introduce quantum model. And if you go to clinicals and you kind of play around with your X-ray tube and you try to introduce quantum model and you can't get it done, just understand that that's because our image receptors are so sensitive now that you might not be able to introduce it. Still testable, so you got to hang on to it, but you might never see it, except for there are some pictures in our different textbooks that show it, especially on very thin anatomy, pediatric chest X-rays, things like that. So quantum model, possible, and it's just because we don't have enough X-rays. So the videos I was talking about, I was at home one day, and we got a detached garage, right? And there's a little sidewalk leading out to the garage, and I look outside, and it started sprinkling. So it started sprinkling. When it starts raining on concrete, what do you see? It's not raining hard enough to soak the concrete, so what do you see? Specks, right? You see specks, right? Now, once it starts raining hard enough to soak the concrete, it goes away. So you get enough quantity of water on the concrete, you don't see the spots anymore. But when you see the spots, quantum model. It's a modelly appearance because of not enough rain yet. Okay, so proportionality to MA. When we're talking about proportionality to MA, it's we can manipulate it, right? So mass is half MA, half time. MA times time creates our mass. So we don't get mass until we make our exposure. So we make our exposure, the electrons travel across the tube, create X-rays, create heat, return to the system. And whenever we get to the end of the exposure, we get a signal sent over to the timer circuit back in the low voltage circuit that kills the exposure, right? So then we have tube current. Until the point of applying kVp, we don't have tube current, we just have filament current. So we don't have mass until we make our exposure. So once we make the exposure, now we've got the number of electrons that travel from cathode to anode and are conducted through the anode. So mass then directly controls the number of photons we create. Now all energy levels, we double our mass and we create exactly twice as many X-ray photons in each one of those energy levels under the brim spectrum. We double mass, we double the output of the X-ray tube. It controls the quantity directly, and always you double the mass, you double the photons. So it controls tube current, controls beam intensity, controls not really optical density anymore, but we're gonna substitute optical density. What we're gonna say is exposure, image receptor exposure. That's what we're gonna use for image receptor exposure correction. So you have a patient, right? So you have a patient is an asthenic patient, and then you have a hypersthenic patient right after that asthenic patient. Theoretically, what you should be doing is, because primarily what you've changed there is adipose tissue, soft tissue, then the patient's going to absorb more of that X-ray beam. So if they absorb more of that X-ray beam, what do you need more of? Not yet. Expect it soon. Expect it sooner or later, eventually. But you took away numbers, so you need to add numbers, right? Mass. So mass is going to be for most of our technique correction, is going to be our go-to technical factor. Unless, we'll get there later. I don't want to complicate it too much right now. So for the most part, it's going to be what we control image receptor exposure with. All right, so in the mass output is, and especially the MA output, not so much mass, but MA output is going to be consistent except for on falling load generators. You remember talking about falling load generators last semester. What we had was a generator that would start out at the highest possible MA station, and throughout the exposure it would drop in order to try to minimize the potential for motion artifact. So you're phototiming, and it would start at maybe 1200 MA, shoot for a while, drop to 1000, drop to 800, drop to 600, and so forth, just to minimize the exposure time. All right, so distance, we tend to not use distance as a way to control the output from the X-ray tube, right? So we primarily use two distances, that's 40 and 72 inches, but the distance that we select is going to necessitate changes in our mass, so it becomes an exposure factor. Right, so it's independent of tube current, and what I mean by that is that whenever you're reading the questions on the test, read the question and consider what the question is asking you. Right, so if I ask you a question that says you shoot an X-ray at 40 inches, now let's remove all variables and say you're doing a portable chest X-ray. You shoot a chest X-ray at 40 inches today, or yesterday, let's say, and you made a good exposure. The patient couldn't sit down, or couldn't sit up, rather. You had to shoot them supine, 40 inches, and then you go back in today and the patient is better, and you can back up 72 inches. Okay, you're gonna use the same technique? No, you're not. All right? Now, let's say we're doing the same patient in the department. Okay, so you make your exposure at 40 inches. You're doing AC joints, let's say. You remember talking about AC joints? Maybe it was on video because we didn't get into bony thorax. But one problem with shooting AC joints is because of the divergence of the central ray at 40 inches, you may project the AC joints off of the image receptor. So I recommend you shoot AC joints at 72 inches so that the divergence of the central ray isn't quite as bad. Okay? So at 40 inches, you make your exposure, project them off, you back up to 72 inches, and you make a second exposure. You haven't done anything. except for make the 2 exposures. Did anything happen with X-ray tube? The answer is no. That's assuming that you set your technique though, okay? So distance is going to be independent of your tube current. So just increasing your distance all by itself is not going to change your tube current. Your technique is still the same. But what do you usually do when you're in the department? You push the button, right? If you're shooting portable, you got to push a lot of buttons, but if you're in the department, you push the button that says AC joints, right? And you shoot at 40 inches, what happens when you mash that button? What all does it set? Do you know? Okay, I'll need to spend some time behind that control panel pushing buttons and seeing what happens. Selecting different techniques, different exam types, and see what happens. Because what happens every time you push a different exam type, it does a lot of stuff. It selects your focal spot size. It selects your photocells, which radiation detectors you're going to use. It selects your kV. It selects your MA. Sets backup time. All that stuff is set with that one little button that says AC joints. Okay? So, again, if you're working in the department, you're probably not going to be setting your technique, right? You're going to push a button and it sets all that stuff for you. So if you make your exposure at 40 inches, you project those things off, your AC joints off, and you back up to 72 inches, now what's going to happen?
Technique was too low?
Technique would be too low, but if you push the button that says AC joints, what all gets set for you?
Everything.
Everything, including radiation detectors, right? So you back up to 72 inches, and what's going to happen? Because you back the patient up to 72 inches, what's going to happen? How do your AECs work? What do they do?
Penetration, remnant beam.
What's that?
Like the remnant beam.
The remnant beam, it picks up the signal in the remnant beam, it counts the photons, and it sends a signal over to the timer circuit to discontinue the exposure, right? So if you back up to 72 inches, if you set your technique, what do you have to do? From 40 inches to 72 inches, what do you have to do? Okay, you're getting ahead of me. I backed up a little bit because I wasn't getting any kind of feedback here. But yes, I'll get there in a second. So you're doing that portable, again, you shoot at 40 inches. Your technique, let's say, is 2 mass at 40 inches. You back up to 72 inches, what do you need? If you double your distance, what happens to intensity? Goes down by a factor of 4. It's inverse square law, right? So to maintain intensity, if you back up, let's say, make it simple and go 80 inches from 40 to 80 inches, what needs to happen with your technique? You used 2 mass before, now you're going to need 2 times 4 is, hey, there you go, is 8, right? So once I changed my technique, did my tube current change? Yeah, it did by a factor of 4, right? So now back to the phototimers. Now you're back in the department, you're making the same exposure. 40 inches, it gives you 2 mass. You back up to 80 inches. What's gonna happen? What's the job of the phototimers?
Terminate. Terminate.
Terminate the exposure when?
When enough has reached them.
Right, so if at 40 inches it gave you 2 mass, at 80 inches it's going to give you 2 times 4 is 8. There you go. All right, so that was a long walk to get to this. Read your questions, all right? So on the test, if it says mass or, distance is independent of tube current, yes? Yeah, absolutely. Or I'm sorry, distance is independent of tube current. You can put any distance that you want to. It's not going to change your output of your X-ray tube unless you do something like introduce phototimers. The purpose for the phototimers is to adjust that mass. As we increase our distance, then tube current's going to have to increase by a factor of 4 if we change from 40 to 80 inches. Right? All right, so if it's independent of tube current, then it's going to be independent of emission, but it does determine the intensity of the image receptor. If we don't change anything except for distance, we get a dramatic change at the image receptor. It's not as dramatic as kVp, but it's dramatic, very dramatic, okay? So double the distance, we have a change in distance by a factor of 2, we have a change in intensity by a factor of 4. Increase our distance, and it's inverse. We increase our distance, our intensity goes down by a factor of 4. We decrease half our distance, and it goes up by a factor of 4. All right, so that was the easy calculation. What is your cheat for changes from 40 to 72 inches? I don't remember. 3.24, right? So if you shoot the perfect X-ray at 40 inches, you go back to 72 inches, you're gonna have to increase your mass by a factor of 3.24.